So we were testing, we got to the critical point, or rather the hypercritical points, which are the critical points from the second derivative, and we got to the part for the test points, the test values rather, not really test points. And well, all these test points we have to test them in f double prime. That means -4 times -2 over -2 squared minus 1 quantity squared. Well, this will be negative into negative, that's positive 8, over -2 squared, which is 4. 4 minus 1 is 3. 3 squared, that's a 9. In this case, well, it doesn't matter what value is this actually. What really matters is whether it's positive or negative. So in this case, we are going to get that this is negative, which means concave up. I mean concave down. Well, oh no, it's positive. Concave up. Now, test -0.5. Testing -0.5, that's a -4 times -0.5 quantity squared. Oh wait, hold on. Oh no, that's fine. Wait. No, that's fine. It's not squared. So that's a negative times a negative. That's also positive. And that's 5 times 4, that's 20. That's actually 2. And 0.5 squared, or negative rather. -0.5 minus 1 squared. Well, whatever that is, we really don't care about what's in the denominator. It's going to be a decimal, a weird number. Yes?
Are we doing first derivative test?
Second derivative test. So the second derivative ends up being -4x over x squared plus x squared minus 1 quantity squared. So we're testing those test values in the second derivative.
That's first derivative. That's fully the first derivative.
Is that the first? Oh shoot, no, that you're right then. So it's not concave up, it's actually increasing, isn't it? I thought we were already in the second derivative. Never mind, thank you.
We are. Just the table says first derivative.
Yeah, first derivative test. Yeah, my bad. Oh yes, it says f prime. Thank you. That's weird. Okay, so that's 2 over positive number. This is positive. It doesn't matter what the number is. All we care is about the sign of the value to determine increasing, decreasing. So in this case is increasing. What about 0.5? That's negative. Oh, actually in f prime. -4 times 0.5 over 0.5 squared minus 1 quantity squared. Well, the numerator, which is -4 times 0.5, that's 2 over whatever number it's in the denominator. It's going to get squared. Whatever that number is, it's going to be a positive number. I don't care about the value, I care about the overall sign, which is plus. And plus. What about, oh, actually negative. Negative over plus, it's negative. And it's actually, well, this is there's something weird here, because according with my results, increasing, oh yeah, no, that's decreasing, that's fine. Decreasing and testing 2 times negative, or rather, -4 times 2 over 2 squared minus 1 squared. That's actually -8 over the same number 9, which is also a positive number. That's going to be overall a negative number. Negative, decreasing. Alright? So this is what we have right here. So let's go back to our number line, where we set the critical numbers. So not the hypercritical numbers. So I should correct that part. It's the critical, not the hypercritical. So increasing, again increasing, decreasing, and decreasing. Well, is -1 going to be a max or a min or nothing? What is that going to be? It's nothing actually, and in fact -1 is one of the vertical asymptotes. It's one of the numbers excluded from the domain. So even if it were increasing, decreasing, or decreasing, increasing, though that value, that critical value, it's actually not in the domain of the function. That's the vertical asymptote. However, between around 0 goes increasing and then decreasing, that means we have a relative maximum. And over here for x equals 1, around x equals 1 goes from decreasing to again decreasing. Well, that doesn't mean anything, and also 1 is one of the vertical asymptotes. So legitimately we only have a relative maximum, we don't have a minimum. And relative maximum that gets evaluated in the original function f of x equals what's that? The original function 2x squared over x squared minus 1. And evaluated at the critical number, which in this case is the only 0 actually. F of 0, that's 2 times 0 squared over 0 squared minus 1, and that's 0 over negative 1, which is 0. And as an order pair, it's going to be the origin, alright? That maximum point will be the origin. No relative minimum because we didn't get a behavior from decreasing to increasing, only a relative maximum. Alright. Second derivative test. So we need to take the second derivative. So what did we get for the first derivative in the first place? Okay, let me write it down again. Negative 4x over x squared minus 1 squared. So first of all, f prime negative 4x over x squared minus 1 quantity squared. Alright, so we need to use the quotient rule. So let's differentiate using the quotient rule. F double prime equals the derivative of the numerator, which is negative 4, times the denominator minus the derivative of the denominator, which in this case, check how this is a composite function. We have an outermost function which is a squared and an inner function which is x squared minus 1. So number 1, in this case we're going to use the chain rule. So 2 times the inside, 2 minus 1, which is 1, times the derivative of x squared, which is 2x, and that times negative 4x, which is the numerator. The whole thing divided by x squared minus 1 squared quantity squared. We squared the denominator. That's going to be, in the end, f double prime. That's negative 4x. I mean, just negative 4. Oh, come on. Negative 4 x squared minus 1 squared minus, okay, so that's going to be x times x, that's x squared, negative times a negative is positive, 2 times 2, which is 4, times 4, that's 16, x squared times x squared minus 1. And well, now the denominator x squared minus 1, 2, or squared, that means multiply the powers, and that ends up being to the 4th power. Alright, we need to simplify this madness in order to set it equal to 0 to find the hypercritical points or values. Well, so how do we simplify this? Well, we're going to do some factoring. Notice how we have x squared minus 1, x squared minus 1. We have powers of them. I mean, the whole numerator has a GCF of x squared minus 1. So we can, in this case, factor 1 power of each, or rather the lowest power, which is power 1, that is f double prime of x equals, I'm going to factor x squared minus 1, that's going to leave us with negative 4 times x squared minus 1 minus 16x squared, and in the denominator x squared minus 1 to the 4th power. That actually simplifies a little bit more because this is an invisible 1 power. Cancel x squared minus 1 to the 1st power with 1 power in the denominator to leave us with 3 in the denominator. Well, so let's keep simplifying the derivative. F double prime will be, number one, negative 4x squared. Negative 4 times negative 1, that's plus 4, minus 16x squared. The whole thing divided by x squared minus 1. Quantity squared. Okay? Or rather, to not squared, actually, to the third power, because we already simplified something in there. Alright, so, well, I'm afraid I did a silly mistake in here. Oh, that's supposed to be a plus right here. Alright, plus. And that's a plus. So 16 minus 4, that's a 12x squared. And, did I do another mistake? Because I was, no, that's fine. That's fine. 12x squared plus 4 over the quantity x squared minus 1 cubed. So that's the second derivative, and again, we have to simplify it all the way. So when we set both numerator and denominator equal to 0, we end up with easy equations to solve. So let's go about the first equation. So that is, I'm going to set the numerator equal to 0, 12x squared plus 4 equals to 0, but in this case, 12x squared equals to negative 4, and x squared equals to negative 4 over 12, which is 1/3. Can we take the square root of a negative number and get a real number? That's along with the I. These are imaginary numbers. We don't want imaginary numbers here. So, well, we can cross out all this. So no critical numbers out of the numerator. However, the critical numbers out of the denominator, for which we will set x squared minus 1 cubed equal to 0. Take the cube root on both sides, that leaves us with x squared minus 1 equals to 0, x squared equals to 1, and x equals plus or minus the square root of 1, which is plus or minus 1. In this case, we have two hypercritical numbers, right? X equals to negative 1 and x equals to 1. Let's plot those values on a number line. Negative 1 and 1. That's going to lead us into 3 intervals to test. So that's why I have 3 columns in our box to test those values. Alright, so that's going to be negative infinity to negative 1, negative 1 to 1, and 1 to infinity. So just as a piece of advice, so when you are given a problem like this on the exam, they're not going to give you a table like this. They're just going to tell you, analyze the function. So my advice is that you guys do these tables on your own, so you can organize all the information just to verify and check for consistency the calculus you do with the calculations and all the remaining properties with the final sketch of the graph, right? So most likely it's going to be a 1-page problem. So, and it's just going to say analyze the function, you do the whole thing, all right? Because the thing is, if they give you a blank table, somehow they're giving away some results, like, oh, there's 2 critical numbers, or if there's 5 columns, oh, there's 5 critical numbers, and that's kind of, you know, too much to give away. Well, let's get some test values. How about negative 2, 0, and 2? Let's go with the easiest value. So test x equals negative 2, x equals 0, and I need a third test. Test x equals to 2. Alright, to test x equals to negative 2, x equals to 0, we test them in the second derivative, which is this madness here. So that's, let me write it down again. That's f double prime. So that's f double prime of negative 2. That's 12 times negative 2 squared plus 4 over negative 2 squared minus 1 cubed. Well, so negative 2 squared equals to 4. 4 times 12 is, what's that? Is that 48? 48 plus 4, well, what's that? Isn't that positive? Let's not care about the numbers anymore. Let's just care about the signs, because ultimately we're testing the end behavior of the function to be positive or negative. So you will not really be graded on the numerical values, but really the signs. So negative 1 squared, negative 2 squared, that's positive 4, minus 1, that's 3. 3 cubed is 27, it's also positive. Positive over positive, isn't that a positive? And well, what about testing x equals to 0? So f double prime at 0, that's a 12 times 0 squared plus 4 over 0 squared minus 1 quantity cubed. Well, 0 squared, which is 0, times 12, that's also 0, plus 4 is positive 4 in the numerator. And in the denominator, be careful, check this out. 0 squared, that's 0. 0 minus 1 is negative 1. But that negative 1 being cubed, is that going to output a positive or a negative value? Negative. Alright, what's positive over negative? Negative. Alright, 2. F double prime at 2. 12 times 2 squared plus 4 over 2 squared minus 1 cubed. So again, it's going to be the same result as before, positive over positive, and that's positive. Check the result I'm getting for negative 2 and for positive 2. I can just go directly to say positive, because didn't we check before that this function is symmetric about the y-axis? So whatever end behavior you get for this value on the left, it's going to be the same behavior on the right. So alright, that means concave up, concave down, and concave up, which means happy face, sad face, happy face. So that goes from concave up, concave down, concave down. Well, does that really imply that we have points of inflection? It's going from concave up to concave down. So our second derivative test tells us that there should be an inflection point at x equals negative 1. And so it tells us that there should be an inflection point at x equals to 1, because there's also a change between concave down to concave up. However, yes, that checks with the second derivative test, but aren't they, these numbers, negative 1 and positive 1, not in the domain of the original function? So no points of inflection, since x equals negative 1 and 1 are not in the domain of f. So yes, everything looks like nice. Wow, it changes the concavity and all that, but again, check with the original results. No change in the concavity at all. Alright, there's a change in the concavity, but really no points of inflection. Alright, so, well, yes, no points of inflection. So how about, okay, NA, how about we plot this graph? Alright, negative 1, negative 2, negative 3, 1, 2, 3, 4, 1, 2, and what else? Let me move it a little down. Oh, come on, not too far. Alright, here's fine. Okay, so number 1, let's plot everything we have. So number 1, I believe if you go back a few pages, we got 2 asymptotes. One asymptote, one vertical asymptote at x equals to negative 1, and another asymptote, vertical asymptote at x equals to 1. Let's draw those asymptotes. So here is one, and here is the other one. Well, we also have a horizontal asymptote for this one at y equals to 2. That is going to be this graph. Alright, so those are the asymptotes in this case. Well, what do we have for, what else do we have? We can use all the information from from the first derivative test to get the graph of this function. All right. Well, the first derivative test told us that there was a maximum, a relative maximum at x equals to 0. All right. So in this case, where is that maximum at? It's right here, the origin. The origin turns out being the maximum value. So that's going to be this point right here. Alright, this point right here. And well, because it has a maximum, it has to look somehow like this. Alright. Critical values were x equals to -1 and x equals to 1, which actually were coincident with what's it called, with the values with the equations of the asymptotes. Now, what about over here and here? We'll find out what it is. Well, let's go back to the first derivative test. It's increasing, increasing, decreasing, decreasing. That means we should have this graph to increase and decrease. So again, increasing, increasing, reaches a maximum, then it goes decreasing and then decreasing. All right. So that's with accordance with the table that we did for the first derivative test. Well, let's draw arrows here to denote that this goes on forever, to denote continuity. Now let's check concavity. In accordance with the second derivative test, concave up, concave down, concave up. All right. Does that look consistent for you? Concave up? I mean, essentially concave up, if you will. Concave down and concave up, if we will. Consistent with everything we did. Looks good. So that's the graph of f of x, roughly. Of course, you can use your graphing calculator and you should see this graph. However, the downside with graphing calculators is that they won't show you asymptotes, neither the vertical nor the horizontal asymptote. So in this case, you still need to input your knowledge about asymptotes and think that those asymptotes are there. Yes, calculators are very smart devices. However, they're not that smart to show you these asymptotes. All right. Let's do one more example. Let's do more examples. So let's analyze the curve f of x equals x e to the x. All right. So domain of the function, I would say right here that's negative infinity to infinity. In other words, all real numbers, because we don't have any radicals of even index. We don't have any what else? Any rationals, any logarithms. However, x, which is a polynomial, is defined for all real numbers. E to the x is defined for all real numbers. So, domain is all real numbers. X-intercept. Let's go a little quicker this time. X-intercept, so set y equals to 0. So, x e to the x. Set it equal to 0, and well, over here, either x equals to 0 or e to the x equal to 0. But in this case, e to the x never goes to 0, only x equals to 0. So the x-intercept here will be 0, 0 as an order pair. What about the y-intercept? For the y-intercept, evaluate f at 0. That's 0 e to the 0, which is simply 0. And again, 0, 0 in this case. In this case, the origin is both the x-intercept and the y-intercept. So symmetry. We need to check f of negative x and to determine whether this is itself f of x or negative f of x. If it's f of x, the original function, then it's going to be symmetric about the y-axis. Otherwise, if it's a negative f of x, this function will be symmetric about the origin. So let's do f of negative x. That's negative x e to the negative x, which is negative x e to the negative x. And in this case, well, this is neither the opposite in sign of the original function nor back to the original function. So in this case is neither symmetry, or no symmetry in this case. All right, no symmetry about the x-axis, no symmetry about the y-axis. All right, asymptotes. Do we have any asymptotes? Well, so okay, let me have a look at the book real quick. I think I have this one. Well, so I don't think there's any. Oh yes, there's a horizontal asymptote for this one. It's going to be a weird one, the way we're going to treat the determination for the asymptote. So, well, vertical asymptotes definitely not, because we don't have variables in the denominator. All right, that's a given. So, no horizontal asymptotes. And well, I mean no vertical, rather, no vertical, not horizontal, vertical. So horizontal asymptotes. Well, for horizontal asymptote, we need to look at the limit, actually a couple of limits. Limit x e to the x approaching infinity, and limit x e to the x approaching negative infinity. I didn't do this for the previous example because that was a polynomial over polynomial. However, when we have exponential functions like this, we need to check the limit at infinity to both sides. Well, this will be infinity e to the infinity, which is infinity. Well, so there's no horizontal asymptote towards the right, right? However, what is this, okay, negative infinity e to the negative infinity e to the negative infinity. Isn't it the same as saying negative infinity over e to the positive infinity, which is negative infinity over infinity? Well, what's this? Isn't that an indeterminate form? So that means we will have to use the L'Hopital's rule in order to compute this limit and in order to be able to find that horizontal asymptote. However, check at the original function. That function is not written as a quotient, so we can take the derivative of the numerator and the derivative of the denominator, right? Well, in this case, how about we write x e to the x as x over e to the negative x? Does that look like a quotient function now, which is equivalent to the original function? All we do is send the exponential down to the denominator with the opposite sign. All right? So we can do the L'Hopital's rule here. So the derivative of x, which is 1, the derivative of e to the negative x is negative e to the negative x. And then in this case, this is 1 over negative e to the negative infinity. Well, negative infinity is positive infinity. E to the positive infinity is infinity. And in this case, that's 0. All right? So 0 will be a horizontal asymptote. How is that going to work? Well, you'll see later when we start sketching the graph. First derivative test, f prime of x. For x e to the x, we need to use the product rule here. The derivative of the first factor, which is 1, times e to the x, plus the derivative of the second factor, e to the x, which is e to the x, times x. Well, that's going to reduce to e to the x plus x e to the x. And well, in order to set this as an equation, how about we simplify a little bit? So x plus 1 e to the x That's an e to the x as a greatest common factor, and at this point we may set that equal to 0. X plus 1 e to the x, set it equal to 0. Well, this table already has 2 columns. That means we're going to have only one critical value. So x plus 1 equal to 0, or e to the x equals to 0. Well, e to the x never goes to 0. No critical values out of that. And x equals to -1 will be the only critical value right here. So let's focus on the first derivative test. So -1 is our critical value. That means this will give rise to 2 intervals to test. Number 1, the interval -infinity to -1, and -1 to +infinity. So taking 2 test values, how about -2 and 0? And let's check for the behavior of this for the first derivative. So test x equals to -2, test x equals to 0. So substituting this into the derivative, f prime evaluated at -2, that's going to be, what was that, x plus 1. So -2 plus 1 e to the -2, well, that's going to be -1 times e to the -2, which is -1 over e squared. Well, in this case, that's a negative number, right? It's a negative number, which means decreasing. And what about at 0? So f prime at 0, that equals to 0 plus 1 times e to the 0. That's 1 e to the 0, which is 1. 1 times 1 equals to 1, which is positive. So that's positive and increasing. So that means increasing. Now let's draw arrows right here to determine the behavior. So it goes decreasing and then it goes increasing. What does that mean? According with the first derivative test, what's that? Is that a max or a min? Min. Relative minimum. Alright? So that relative minimum, we are going to find it in the original function. So no max, but relative minimum, that's on f of x, on the original one, on the original function, -1. That's a -1 times e to the -1, which is -1 over e. Alright? And the approximated value for that minimum value, let me get it from, it's approximately -0.37. That is the order pair -1, -0.37. Let's do the second derivative test. For the second derivative test. So f double prime would be the derivative, so the first derivative, which is x plus 1, e to the x. Let's take the second derivative. So the derivative of x plus 1, which is 1 times e to the x, plus the derivative of e to the x, which is itself, times x plus 1. Alright? So what are we going to get out of this? Number 1, we need to simplify this second derivative. So when we set it equal to 0, we end up with an easy equation to work with. Alright, number 1. I'm going to factor this e to the x, f double prime, that's e to the x times 1 plus x plus 1. And 1 plus x plus 1, that's going to give us f double prime e to the x times x plus 2. Or let me write down the x plus 2 first, just to be consistent with the notation I used before. Alright, either way it's the same anyway. So that's the second derivative. Let's set the second derivative equal to 0. X plus 2 times e to the x equals to 0. That's x plus 0, x plus 2 equals to 0, and e to the x equals to 0, x equals to negative 2, and well, e to the x never goes to 0. So the only hypercritical value we're going to get is x equals to negative 2. All right? So that's going to give rise to 3 intervals to test. Negative infinity to negative 2, negative 2 to infinity. So let's pick our test values. And a good test value here will be, well, negative 3. And a good test value, how about x equals to 0? Go with the easiest values to test. And again, we test these two values in f double prime. So, test x equals to negative 3, test x equals 0. So, testing in f double prime, that's negative 3. That's negative 3 plus 2, e to the negative 3, that's negative 1 times e to the negative 3, which is negative 1 over e cubed. And testing at x equals to 0, f double prime at 0, that's 0 plus 2, e to the 0, that's 1 times 2, that's 2. In this case, negative, positive. Well, negative and positive for the second derivative, that means concave down and concave up. So, concave down here, concave up, that means there is a point of inflection. Well, in this case, that hypercritical value of x equals to negative 2, it's a number in the domain of the original function. So this will be legitimate, in this case, a point of inflection. And that point of inflection will be evaluated in f of x. So f at negative 2, that's negative 2 e to the negative 2, which is negative 2 e over e squared, which is approximately negative 0.27. In other words, the order pair involved is negative 2 comma negative 20, negative 0.27. All right. Okay. So we have all the information actually to graph this function. So let's make this a little big, and that's a negative 1, negative 2, negative 3, 1, 2, 3, and well, 1, 2, 1, 2. All right, so number 1, we have an x-intercept at the origin. That is. Okay, so what else do we have? So from the first derivative test, let me check at the summary. Oh, we also have a horizontal asymptote towards negative infinity. That is, it's going to look like this dashed line overlapping the negative x-axis. All right, it's going to look like this. I'm going to draw it a little out of phase so you can distinguish between the negative x-axis and the actual asymptote. So that's the asymptote. Then we have a minimum at the point negative 1 comma negative 0.37. So negative 1, negative 0.37, which is roughly here. That's a minimum point. All right, and then what else do we know about? Well, they're telling us that, okay, so from this minimum, that means it has to look like this, right? It has to have this behavior because it's a minimum. It goes from decreasing to increasing, and it actually increases all the way from negative 1 all the way to infinity. So let me draw this better. So it's going to increase all the way, And well, over here is increasing. Now, concavity. They're telling us it's concave down before -2 and concave up after -2. All right, so from here, it's going to change to concave. So this is basically our concave down part, and this is our concave up part of our graph. Is that consistent with everything that we got from the second derivative test? And well, in this case, this is going asymptotically to 0, but never actually touching the 0. So this is a good rough sketch of the graph. So you have to show this point of inflection, this minimum point, increasing, decreasing, etc. So this is it for today. So I'm not sure we're gonna get the chance to cover one more example I had in plan. So let's just leave it over here. Right. Have any questions? I'll be around a couple minutes. Otherwise, have a great day. I will see you on Friday.
This part, the horizontal asymptote is zero.
Yes.
How does this go across here?
So in this case it goes across the intercept, but it goes to positive infinity. So there's no horizontal asymptote behavior towards the positive side, only the negative side.
How do we know?
Because we evaluate for horizontal asymptotes, we need to evaluate the limit at both positive infinity and negative infinity.
Oh, so it goes here and then left it goes here.
Exactly.
Oh, that's why. Thank you.
If you could wait for me, I'll take communication class.
Oh, I have one more.
Yes.
In this part, you use L hospital.
That's the derivative of the numerator, the derivative of x, which is 1, and the derivative of e to the negative x, which is negative e to the negative x. I think we forgot to write the negative by mini changing.
My question is like here, like can't we just do like this one over 1 and then just quotient rule?
No, we don't use quotient rule. L'Hopital's rule is the derivative of the numerator over the derivative of the denominator. And while this given function is not a quotient function, the trick is to send the e to the x to the denominator with negative exponent. That's going to be for the Alright?
I think the hardest one is the asymptote.
Yeah, that was a tricky one because in this case we're dealing with an exponential, not with a polynomial over polynomial, which is going to give us the same horizontal asymptote in this case, on both sides, whether it's positive or negative infinity. Alright?
Thank you.
My pleasure. Ok, mira, lo único que sí, mira, el único problema que tengo es que no los puedo subir luego